Welcome! Today, we'll be tackling LeetCode problem number 1646, titled Get Maximum in Generated Array. This problem challenges us to generate an array based on specific rules and then find the maximum value within it. Let's dive in and explore the solution step by step. In this problem, you're given an integer n, and your goal is to generate an array nums based on specific rules. The array is zero-indexed and has a length of n plus 1. The first two values are defined as nums, 0 equals 0 and nums, 1 equals 1 if n is at least 1. For higher indices, the values are determined based on whether the index I is even or odd. If I is even, the value at that index is simply copied from nums, I/2. If I is odd, the value is the sum of nums, I/2, and nums, I/2 plus 1. Once the array is generated, the task is to return the maximum integer in the array nums. The input to the problem is an integer n within the range 0 to 100, and the output is a single integer representing the maximum value in the generated array. Let's look at the first example, where n equals 7. The goal is to generate the array nums as described. Starting with the initial values, nums, 0 equals 0 and nums, 1 equals 1. Next, for I equals 2, since 2 is even, we calculate nums, 2 equals nums, 2/2 equals nums, 1 equals 1. For I equals 3, which is odd, we calculate nums, 3 equals nums, 3/2 plus nums, 3/2 plus 1 equals nums, 1 plus nums, 2 equals 1 plus 1 equals 2. These calculations follow the defined rules for generating the array. Continuing the example for n equals 7, we calculate the next values in the array. For I equals 4, since 4 is even, nums, 4 equals nums, 4/2 equals nums, 2 equals 1. For I equals 5, which is odd, nums, 5 equals nums, 5/2 plus nums, 5/2 plus 1 equals nums, 2 plus nums, 3 equals 1 plus 2 equals 3. Moving to I equals 6, an even number, we have nums, 6 equals nums, 6/2 equals nums, 3 equals 2. Finally, for I equals 7, an odd number, nums, 7 equals nums, 7/2 plus nums, 7/2 plus 1 equals nums, 3 plus nums, 4 equals 2 plus 1 equals 3. The resulting array is nums equals 0, 1, 1, 2, 1, 3, 2, 3, and the maximum value in this array is 3. Now, consider the second example, where n equals 2. Here, the task is to generate the array nums for the smaller value of n. Starting with the rules, nums, 0 equals 0 and nums, 1 equals 1. For I equals 2, since 2 is even, nums, 2 equals nums, 2/2 equals nums, 1 equals 1. This gives us the array nums equals 0, 1, 1. The maximum value in this array is 1. For another example, when n equals 0, the array nums contains only one element, nums, 0 equals 0. Therefore, the maximum value is 0. Finally, let's review the constraints and edge cases. The input n determines the size of the array as n plus 1, meaning the length of nums ranges from 1 when n equals 0 to 101 when n equals 100. For smaller values of n, like 0, 1, or 2, the computations are straightforward, making these edge cases simple to handle. For larger values, such as n equals 100, the rules ensure that the array can be generated efficiently by leveraging the recursive relationships between elements. With a maximum size of 101, the problem constraints ensure that the solution is computationally feasible and does not require excessive resources. To solve the problem of finding the maximum value in a generated array, we first need to understand how the array is constructed. The array nums is generated based on specific rules. For any index I, the value of nums, I, depends on whether I is even or odd. If I is even, nums, I, is equal to nums, I/2. If I is odd, nums, I, is the sum of nums, I/2, and nums, I/2 plus 1. With this in mind, one straightforward approach is to construct the array step by step and keep track of the maximum value as we go. This method starts by initializing nums, 0, and nums, 1, and then iterates through indices from 2 to n, calculating each value based on the rules provided in the problem. The time complexity is O, n, because we process each index once, and the space complexity is also O, n, because we store the entire array. While simple and direct, this approach has its limitations, especially in terms of memory usage when n is large. One downside of the brute force generation approach is that it requires storing the entire nums array in memory, even though we may only need the maximum value. To address this, an optimized space approach can be used. Instead of maintaining the full array, we calculate values on the fly and only store the minimum number of variables needed for the current computation. This drastically reduces the space complexity to O(1), as we no longer allocate memory for the entire array. The method involves using two variables to keep track of the current and previous values required for computation. Each nums, I, is calculated as needed, and the maximum value is updated directly. The time complexity remains O(n), as we still process each index once. However, this method involves slightly more complex logic to manage the calculations without storing all intermediate results. It's also limited to scenarios where the full array isn't needed, making it less versatile than the brute force approach. Another option is a recursive solution with memoization. This approach leverages recursion to calculate nums, I, storing previously computed values in a dictionary to avoid redundant calculations. The recursive function is defined with base cases for nums, 0, and nums, 1, and the formula is applied recursively for other indices based on whether I is even or odd. Memoization ensures that each value is computed only once, making the time complexity O(n). However, the space complexity is also O(n), due to the memoization dictionary and the additional overhead of the recursive call stack. While this method is efficient in terms of avoiding repeated computations, it introduces complexity due to the recursive structure and the need for additional data structures. This makes it less suitable for a problem of this simplicity, especially when iterative solutions can accomplish the same result more straightforwardly. After evaluating the different approaches, the brute force generation method emerges as the most suitable strategy for this problem. Its simplicity and direct implementation of the problem's rules make it easy to understand, debug, and maintain. With a time complexity of O(n) and a space complexity of O(n), it performs efficiently within the given constraints, where n can be at most 100. Additionally, this approach generates the full nums array, which might be useful if the problem requirements were expanded to include returning the array itself. While the optimized space approach is more memory efficient, its added complexity makes it less appealing for a problem of this scale. Similarly, the recursive solution with memoization introduces unnecessary overhead for what is fundamentally a straightforward computation. By avoiding these trade-offs, the brute force approach strikes the right balance between clarity, efficiency, and flexibility. The chosen solution involves iteratively constructing the nums array while keeping track of the maximum value. This ensures that the implementation is both efficient and easy to follow. The process starts by initializing the first two elements of the array and iterating through indices from 2 to n. For each index, the value of nums, I, is calculated based on whether the index is even or odd, and the maximum value is updated as we go. Finally, the maximum value is returned as the result. Here is the Python implementation of the solution. Class solution, def get maximum generated, self, and if n equals 0, return 0 nums equals 0, asterisk, n plus 1, nums, 1 equals 1 max underscore val equals 1 for I in range, 2, n plus 1 if I % 2 equals 0, nums, I equals nums, I ///2, else, nums, I equals nums. I //2 plus nums, I //2 plus 1, max underscore val equals max underscore val, nums, I, return max underscore val. This code directly applies the brute force approach, ensuring the solution is both efficient and easy to implement. In this problem, we are tasked with generating an array nums based on a set of given rules and then finding the maximum value in that array. The rules for constructing nums are as follows. The first two values are predefined, with nums, 0, equal to 0 and nums, 1, equal to 1. For any index I greater than or equal to 2, if I is even, the value at nums, I, is equal to nums, I/2. If I is odd, the value at nums, I, is the sum of two adjacent values, nums, I/2, and nums, I/2 plus 1. Our ultimate goal is to determine the maximum value in the nums array for a given non-negative integer n. This involves both generating the array and identifying the largest value efficiently. To solve the problem, we need to systematically generate the array nums up to the given index n and track the largest value along the way. First, we handle the simple base cases. If n is 0, the array contains only 0, and the maximum value is clearly 0. Similarly, if n is 1, the array is 0, 1, and the maximum value is 1. In both cases, we return the maximum value directly. For larger values of n, we start by initializing the data structures. We create an array nums of size n plus 1 to store values for all indices from 0 to n. The first two values, nums 0 and nums 1, are initialized to 0 and 1, respectively, as specified in the problem. Additionally, we maintain a variable max_value to keep track of the highest number encountered during the computation, starting with an initial value of 1. The next step is to iteratively construct the nums array and simultaneously update the maximum value. Starting from index 2 and going up to n, we compute each value in nums based on the specified rules. If the current index I is even, the value at nums I is set to nums I/2. For odd indices, the value at nums I is calculated as the sum of nums I/2 and nums I/2 plus 1. After computing nums I, we compare it with the current max_value and update max_value if the new value is larger. This process ensures that we determine the maximum value as we build the array, avoiding the need for a separate pass to find it later. Once the loop completes, max_value holds the largest value in the array, and we return it as the result. There are a few key insights that make this approach efficient. First, the pattern in how the array is constructed allows us to derive each value based on previously computed values. For even indices, the computation is particularly straightforward, as it directly reuses a value from an earlier index. For odd indices, the use of two adjacent values ensures no redundant calculations. Another important aspect is the efficient tracking of the maximum value. By updating max_value during the iterative construction of the array, we eliminate the need for a second scan of the array, significantly improving performance. Lastly, the algorithm explicitly handles edge cases like n equals 0 and n equals 1, ensuring correctness for all valid inputs. The solution relies on two primary data structures to achieve its goals. The nums array is the main structure, used to store the values generated according to the problem's rules. Its size is n plus 1 to accommodate indices from 0 to n, and it supports the dynamic programming approach by storing intermediate results for efficient computation. The second key data structure is the max_value variable, which keeps track of the largest number encountered during the array construction. This avoids the need to rescan the array after it is built, making the solution more efficient. Together, these components enable a clear and optimal implementation of the algorithm. Analyzing the algorithm's complexity, we find it to be efficient in both time and space. For time complexity, the loop iterates from index 2 to n, with each iteration involving constant time operations like arithmetic and comparisons. As a result, the overall time complexity is O(n). For space complexity, the nums array requires O(n) space to store the generated values, which dominates the memory usage. Thus, the overall space complexity is also O(n). This makes the solution suitable for handling moderately large values of n within the constraints of the problem. To better understand the algorithm, let's go through an example with n equals 7. We begin by initializing the nums array with 8 zeros, setting nums 0 equals 0 and nums 1 equals 1. The max_value is initialized to 1. Starting from I equals 2, we compute each value step by step. For I equals 2, being even, nums 2 is assigned nums 1, which is 1. The max_value remains 1. For I equals 3, an odd index, nums 3 is the sum of nums 1 and nums 2, resulting in 2, and we update max_value to 2. At I equals 4, another even index, nums 4 is assigned nums 2, which is 1, with no change to max_value. For I equals 5, nums 5 is the sum of nums 2 and nums 3, giving 3, and we update max_value to 3. At I equals 6, nums 6 is assigned nums 3, which is 2, with no change to max_value. Finally, for I equals 7, nums 7 is the sum of nums 3 and nums 4, resulting in 3, with no further update to max_value. The final nums array is 0, 1, 1, 2, 1, 3, 2, 3, and the maximum value is 3, which we return as the output. This Python implementation solves LeetCode problem number 1646, get maximum in generated array. Let's go through the solution step by step. The function getMaximum generated accepts an integer n as input. The goal is to generate an array nums following the rules specified in the problem and return the maximum value in the array. First, we handle the edge case where n is 0. Since nums will only contain the value 0 in this case, we directly return 0. Next, we initialize the nums array with n plus 1 elements, all set to 0. The first two elements of the array are set based on the problem's rules, nums 0 equals 0 and nums 1 equals 1. We then iterate over the range from 2 to n, inclusive, to compute the values of nums based on the rules. If the index I is even, nums I is assigned the value of nums I/2. If the index I is odd, nums I is calculated as the sum of nums I/2 and nums I/2 plus 1. After constructing the array, we use Python's built-in max function to find and return the maximum value in nums. This approach ensures that we compute the result efficiently, with a time complexity of O, n, and space complexity of O, n. The code is concise, handles edge cases, and adheres to the problem's constraints. This is the Java implementation of LeetCode problem number 1646, get maximum in generated array. The logic mirrors the Python implementation, with adjustments for Java syntax such as type declarations and the use of arrays. The function creates an array to generate the sequence and calculates the maximum value during the process. Key differences include the use of math.max for finding the maximum and explicit array initialization in Java. To begin, let's consider the simplest case where n equals 0. The input is 0, and since the problem states that no array needs to be generated when n is 0, we immediately return 0 as the output. There's no need to initialize any array or perform any calculations in this case, making it very straightforward. The output for this input is simply 0. Now, let's look at the case where n equals 2. The input is 2, so we initialize an array called nums with a size of n plus 1, which translates to a size of 3. Initially, all elements in this array are set to 0, giving us 0, 0, 0. Next, we manually set nums 1 to 1 based on the problem's rules, updating the array to 0, 1, 0. Then, we start the loop with I equal to 2. Since 2 is even, we calculate nums 2 as nums 2/2, which is nums 1. Since nums 1 is 1, we update nums 2 to 1, and the array becomes 0, 1, 1. At this point, the loop ends because we've reached n, so we move to the final step, which is finding the maximum value of the array. The maximum of 0, 1, 1 is 1, so the output for this input is 1. Now let's tackle a slightly more complex example where n equals 7. We start by initializing the nums array with a size of n plus 1, which is 8. Initially, all elements are set to 0, so the array looks like 0, 0, 0, 0, 0, 0, 0, 0. Then, we manually set nums 1 to 1, updating the array to 0, 1, 0, 0, 0, 0, 0, 0. The loop begins with I equal to 2. Since 2 is even, we calculate nums 2 as nums 2/2, which is nums 1. Since nums 1 is 1, we update nums 2 to 1, resulting in the array 0, 1, 1, 0, 0, 0, 0, 0. For I equal to 3, which is odd, we compute nums 3 as nums 3/2 plus nums 3/2 plus 1, which is nums 1 plus nums 2. Both are 1, so nums 3 becomes 2, updating the array to 0, 1, 1, 2, 0, 0, 0, 0. Next, for I equal to 4, which is even, nums 4 is calculated as nums for /2, which is nums 2. Since nums 2 is 1, we update nums 4 to 1. Continuing from there, the array after updating nums 4 becomes 0, 1, 1, 2, 1, 0, 0, 0. For I equal to 5, which is odd, we calculate nums 5 as nums 5//2 plus nums 5//2 plus 1, which is nums 2 plus nums 3. Since nums 2 is 1 and nums 3 is 2, nums 5 becomes 3, and the array updates to 0, 1, 1, 2, 1, 3, 0, 0. For I equal to 6, which is even, nums 6 is computed as nums 6//2, which is nums 3. Since nums 3 is 2, nums 6 is updated to 2, and the array becomes 0, 1, 1, 2, 1, 3, 2, 0. Finally, for I equal to 7, which is odd, we calculate nums 7 as nums 7//2 plus nums 7//2 plus 1, which is nums 3 plus nums 4. Since nums 3 is 2 and nums 4 is 1, nums 7 is updated to 3, and the array becomes 0, 1, 1, 2, 1, 3, 2, 3. To wrap up this example, we now compute the maximum value in the final nums array, which is 0, 1, 1, 2, 1, 3, 2, 3. Among all the elements, the maximum value is 3. Therefore, the output for n equals 7 is 3. This example demonstrates the way the array evolves based on the even and odd indices and how the final maximum value is derived from the completed array. To analyze the time complexity of our solution, let's break it into 3 main steps. First, we have the initialization of the nums array, which requires us to allocate memory for n plus 1 elements. This operation is linear in time and takes n. Next, we have the process of filling the array. Here, a for loop iterates from I equals 2 to I equals n, and for each iteration, we perform a conditional check and an assignment. Both of these operations are constant time, 1, and since the loop runs n1 iterations, filling the array contributes n overall. Lastly, we need to find the maximum value in the array using the max nums function. This requires a single traversal of the array, which again takes n time since the array has n plus 1 elements. When we combine these steps, we see that all parts contribute linearly to the time, leading to an overall time complexity of n. Adding up the time complexities from each step, we get n plus n plus n, which simplifies to n. Now, looking at the space complexity, the primary memory usage comes from the nums array. Since it is allocated to hold n plus 1 elements, this requires n space. Besides that, we only use a few auxiliary variables, such as I for the loop and temporary variables during the max nums operation. These variables consume constant space, 1. Since no other data structures are used, the total space complexity is the sum of n for the array and 1 for the auxiliary variables, which simplifies to n. When comparing this optimized solution to a brute force approach, we see a significant improvement. A naive method would involve recalculating each nums I value on demand, potentially using recursion. However, this would result in repeated calculations for the same indices, leading to an exponential time complexity of 2 to the power of n. In contrast, the solution we've implemented uses dynamic programming to pre-compute all values in the nums array. This ensures that each value is calculated only once and avoids redundant computations. As a result, the time complexity is reduced to n. If we analyze the operations in detail, the for loop runs n1 iterations, each taking constant time, contributing n. The max nums operation, which involves traversing the array once, also takes n. Since these are the only significant contributors, the overall time complexity is n. Similarly, the space complexity remains n, due to the nums array being the only significant consumer of memory, with no additional data structures used. Now, let's look at the best, average, and worst case scenarios for this algorithm. In the best case, when n is 0 or 1, the for loop doesn't execute at all, and the solution directly returns 0 or 1. This results in a constant time complexity of 1. For the average and worst cases, when n is larger, the algorithm must execute all operations, including iterating through the array, filling it, and finding the maximum value. These operations collectively result in a time complexity of n, which remains consistent regardless of the input size beyond the best case. This makes the solution efficient and predictable in its performance. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases like n equals 0 or n equals 1 is a frequent oversight. For n equals 0, the array nums only contains one element, which is 0, so the maximum is also 0. For n equals 1, the array becomes 0, 1, and the maximum value is 1. Overlooking these scenarios can lead to incorrect results. Second, there's the issue of incorrect index calculations, particularly for odd indices. The formula for nums, 2 I plus 1, is nums, I, plus nums, I plus 1, but errors like using nums, I, plus nums, I, instead are quite common and will produce incorrect outputs. Lastly, inefficient memory usage can be a problem. Some solutions unnecessarily allocate the entire nums array up to n, even when only a few indices are accessed, which can cause memory inefficiency, especially when n is large. Optimizing memory usage by storing only the values needed for the computation is crucial for efficiency. Another frequent mistake is misunderstanding the recursive relationship that defines the problem. The recurrence relations are clear: nums, 2 I, is equal to nums, I, and nums, 2 I plus 1, is nums, I, plus nums, I plus 1. Misinterpreting or modifying these relations, such as trying to interpolate values or create new patterns, will result in incorrect arrays. Additionally, some solutions use brute force without any optimization. Generating the entire array for all values of I without leveraging the recurrence relation leads to redundant calculations and unnecessary computational overhead, which increases the time complexity significantly. Efficiently applying the given relationships is key to solving the problem effectively. From an interview perspective, this problem is designed to test several important skills. First, it evaluates your ability to recognize and implement recurrence relations, which is a common theme in algorithmic problem solving. Identifying how subproblems relate to each other is crucial here. Next, it's important to optimize your solution based on the problem constraints. For instance, since n is constrained between 0 and 100, an iterative approach is efficient, but discussing trade-offs for larger inputs can show deeper critical thinking. Another crucial point is handling edge cases like n equals 0 and n equals 1. Explaining these cases clearly in an interview demonstrates attention to detail and robustness. This problem is also closely related to dynamic programming, specifically bottom-up approaches. Many interviewers use it to assess your understanding of minimizing time and space complexity. To prepare further, you can explore related problems like LeetCode 70, 198, 1137, and 509, which all involve recurrence relations or dynamic programming concepts. There are several approaches to solving this problem, each with its own trade-offs. The most efficient is the iterative approach, where you generate the nums array using a loop and calculate each value directly based on the recurrence relations. This method has a time complexity of O, n, and a space complexity of O, n. For even better space efficiency, you can use an optimized space approach. Instead of storing the entire nums array, you only maintain the last 2 or 3 values needed for computation. This reduces the space complexity to O, 1, while preserving the O, n, time complexity. Another option is the recursive approach, where you implement the recurrence relation recursively. However, this method is inefficient due to redundant calculations, resulting in exponential time complexity. You can improve it with memoization, which reduces the time complexity to O, n, but it still has higher overhead compared to the iterative method. Lastly, there's the brute force approach, where you generate the entire array without using the recurrence relation. This approach is the least efficient, as it involves unnecessary computations and increased resource usage. Understanding these alternatives helps you choose the best strategy based on the problem requirements and constraints. Great job! We've walked through the solution to the get maximum and generated array problem. Remember, mastering array manipulation and understanding constraints is key for similar challenges. Thanks for watching, and don't forget to like and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!